Swayam Prabha. Digital India. Educated India.
So, last class I have discussed about how I will get the CRR 7.5 by using CPT data, then the shear wave velocity data, and I was discussing about the different correction factors and the magnitude correction factor, then correction factor due to the presence of static shear stress, and the correction factor due to overburden pressure when the effective overburden pressure is greater than 100 kPa. And now and I have discussed in detail about the Kc, K alpha and the K sigma. The K alpha is the correction factor due to the presence of static shear stress, and K sigma is the correction factor due to effective overburden pressure. Okay. And now I will start today's class. I will first discuss about the magnitude correction factor or scaling factor. Now, before I start to the magnitude correction factor, in my previous lecture I have given this is sigma v dash. Actually it is sigma v. Okay, so that was written, it is sigma v, and this one is sigma v dash. Okay, similarly here also it is sigma v0 total, and this one is the effective. Okay, so now I will discuss about the magnitude correction or the scaling factor. Okay, so this magnitude scaling factor in this this is the earthquake magnitude, and these are the scaling factor. X axis is earthquake magnitude, or y axis is the scaling factor or the correction factor. Now, in the workshop, this shaded line, this is the zone is been recommended, because different researchers are given different value of magnitude scaling factor, but in the workshop that we are summarizing here is given this zone is the recommended zone, or we can use this expression to get the magnitude scaling factor. And this seed and Idris has given magnitude scaling factor value. Idris also given this number magnitude scaling factor value for different magnitude, because it is 7.5, it is should be definitely 1 for all the cases. But if it is more than 7.5, then your factor of safety will actually decrease. You can see it will be greater less than 1.5, but because it is developed for 7.5, so now if I design it for greater than 7.5, the factor of safety will decrease. But if it is designed for less than 7.5, then the factor of safety will increase. So that is the thing you can see. If it is 6, then the value is around 2. If it is 6, then the magnitude scaling factor is around 2 from the recommended zone. But here for 6 it is 1.32, this has given 1.76. So now we will use this shaded zone that is been recommended, or you use this equation, okay, to get the magnitude scaling factor. So now all these three corrections are been discussed. Now the very important question is how we will select the Amax. In the last week class I was discussing that we can use the available empirical equations to get the, or correlations to get the Amax or PHA, peak horizontal acceleration. But you have to remember that those should be the ground surface acceleration. If not, if suppose you are getting the acceleration which is the bedrock acceleration by using the correlations, then you have to do the ground response analysis, and then you will get the ground surface motion or the response, and or ground surface motion, and from there you will get the ground surface acceleration. So can be estimated from the local site response or ground response analysis, okay, or site response analysis. And this Amax also you can use, you can do the, I have already discussed in this previous module, that you can do the seismic hazard analysis also, and to get the, or using those correlations or attenuation relations that are given. So you can use them, proper attenuation relation for the site which where you are designing, or you are calculating, or you are assuming that Amax. So you do the proper, use the proper attenuation relationship, for appropriate attenuation relationship for your site, and you can do the seismic hazard analysis and get the Amax value. And if that Amax is for ground surface Amax, then okay, you can use it. But if it is not that, then you have to do the site response analysis to get the ground surface Amax. IS code 1893 part 1 2016 has recommended that if PGA or PHA or Amax is not available, then Amax by G should be taken as seismic zone factor. Because we know that in our IS code, our whole country is divided into 4 zones. So those seismic zone factor Z we can use at Amax by Z. Amax by G. What are those factor? So zone 2 it is 0.1. Zone 3, 5 zones actually. There are 5 zones. So if zone 2 it is 0.1, zone 3 it is 0.16, zone 4 it is 0.24, and zone 5 it is 0.36. So that is also recommended. If that you have not done any analysis, you don't have any Amax by G value, then you can use this one for your design. That is recommended by IS 1893. So now, as I mentioned, that sometimes if the your dissipated pore water pressure is not allowed, I mean your generated pore water pressure is not allowed to dissipate fully under condition, then some gravelly soil can also be liquefied. But the liquefaction resistance of non-gravelly soil can be evaluated through CPT, SPT. That I know, and that we know, and we have already discussed that. But liquefaction resistance can also be done with the occasional measurement of VS value. That also been discussed. But CPT and SPT measurements are not generally reliable for gravelly soil. So then for gravelly soil, which test we will do? We will do the BTP, Baker penetrometer test. So we will do the Baker penetrometer test if it is a gravelly soil, because that also sometimes liquefy. So that also you have to check. Now how we will check that? We will use the same technique that we discussed about the CPT, but we have to convert this BPT to CPT value. How we will do the convert? So corrected Baker blow count N value, and that we can use this chart and curve, and then we will get the corrected SPT blow count at N160 or N60 blow count per feet. Clear? So if I use this chart, then from the BPT I will get the SPT value, and that SPT I can use to get the liquefaction resistance. Clear? So now we have discussed all the procedure. Now let's solve some example problem. Then we will see how these equations can be used. Okay. So like I have given one example problem in my previous week lecture, where actually those datas are available for different depth. So say 1 meter interval or 1.5 meter interval, depending upon your requirement. So datas are available with different depth, and we have to check that liquefaction possibility for every depth, and then we can identify the up to which the liquefaction will occur, or the zone of liquefaction. So every depth we will do it. We can check. So I am giving you 2 depths, and then based on the 2 depth data, the data of these 2 different depths we will check, and similar way you can check it for any depth for n number of data. Clear? So the data, first we will use the SPT. We will use the SPT. Okay. So depth, so the first depth that we will check is 4.5 meter from the ground surface, where my N160 value is given for is 16. That means N value is been measured at 4.5 meter depth for particular site, then it is been normalized and converted to 60% hammer efficiency. So that means N160, first is measured data, then it is been converted to N160, and conversion procedure I have already discussed in my SPT lecture. So you can convert it, you will get the N160. So, and the fine contents of that at 4.5 meter, that is also measured at 10%. We are designing it for magnitude of earthquake 7.5 with a max by G value of 0.2. Okay. Now water table is two meter below the ground level. That means this is the ground, this is the water table. It is 2 meter and my site is here, sir, at 4.5 meter. Okay, and here my location or the depth is 4.5 meter on that site. So, and the same gamma bulk and gamma set value we will consider, that we considered in my previous example during when I check the liquefaction possibility by using laboratory test data. Gamma sat (20 kilonewton per meter) and gamma W is 10 kilonewton per meter cube. Gamma sat is 20 kilonewton per meter cube. Okay, so first we will calculate CSR. That means the stress required or stress is developed during an earthquake. So that you know, that is 0.65 into A max by G into sigma V divided by sigma V dash, or sigma V0 divided by sigma V dash 0. Okay, you can write 0 or you can write sigma V, both are same because I am using different notation in different time. Okay. Both will be treated as initial effective overburden pressure, and this is RD. So what RD value I will consider at 4 meter, you can see. So I will use these equations actually to get the RD. It is 4 meters, so I will use the equation, first equation. Okay. So I will use my first equation. So the RD expression is equal to 1 minus 0.00765 into Z. Z is 4.5 meter. So this equation is valid if RD Z is less than 9.15 meter. So it is the case. So it is, we will get 0.966. So my sigma V value or sigma V0 is equal to total 2 into 18 plus 4.5 into 20. Okay. Sorry, it is 2 into, it is 2.5. It will be 2.5. It will be 2.5 into 20. So it will be 86 kilonewton per meter square. Similarly, sigma V dash effective, it will be 2 into 18 plus 2.5 into 20 minus 10. So it will be 61 kilonewton per meter square. Okay, so CSR value will be 0.65, Max by Z is 0.2, sigma B is 86 and sigma V dash is 61, and RD is equal to 0.966. So this is equal to 0.177 or 0.18. Okay. So now I will calculate the CRR. So to calculate, now there is a 10% fine. So now we have to convert this N160 to N160 clean sand, because now it is N160 is not clean sand. So its fine is there 10%. This is the without conversion data. Before conversion, this data is, this is that data. So what I will do the conversion N160 clean sand, 60 clean sand, that is equal to alpha plus beta N160. Okay. Now it is in between that 5 to 35%. So because it is 10%, so my alpha value will be EXP 1.76 minus 119 divided by fine content square. So that is equal to exponential 1.76 minus 190 divided by 10 square. Fine content is 10%. So that is equal to 0.87. Similarly, beta value is equal to 0.99 plus fine content 1.5 thousand. So that is equal to 0.99 plus fine content is 10 to the power 1.5 divided by 1000. So that is 1.022. So N160 clean sand is alpha is 0.87 plus beta is 1.022 into 16. That is N160 16. So this is coming out to be 17.222. Roughly I will round up it to 17, but you can take 17.222 also, because if I round up it to 17, reduce it, so that means you are in the safe side. Yeah. So it is not issue, but you can take 0.722 also. So we will get N160 clean sand. Now I will calculate CRR 7.5, which is equal to that 1 by 34 minus N160 clean sand, N160. Clean sand, okay, plus N160 clean sand divided by 135 plus that is plus your okay, so that is 50, then that equation is given here. So I will, let me check that equation. Yeah, 50 plus 50 by minus 1 by 200. Okay. So plus 50 divided by 10 into N160 clean sand plus 45 whole square minus 1 by 200. So I will put 34, N160 clean sand is 17 plus this is 17, 135 plus 50, then 10 into 17 plus 45 square minus 1 by 200. So this is coming out to be 0.181. Okay. So my factor of safety, now your factor of safety value, factor of safety FS is CRR 7.5 divided by CSR into magnification scaling factor into K sigma into K alpha. Now here magnification scaling factor, it is for 7.5 magnitude. So your magnification scaling factor is equal to 1 as MW itself equal to 7.5. Now K sigma will be equal to 1 as sigma V dash or V0 dash is greater than 100 kPa. It is, you can see, the sigma V0 dash is how much? 61, which is less than 100 kPa, so no correction is required. And sigma alpha, K alpha, this is sigma, alpha is also 1 because it is not a sloping ground, it is a flat ground and no such loading is also applied. Okay, we are checking it for without any loading or structure. So or it is not a sloping ground also. So the static shear stress ST, so here it is not existing. So we are not considering the effect of presence of the static shear stress because it is not existing. So we are assuming that it is 0. So now if this is the case, then our value will be 0.181 divided by 0.177 into 1 into 1 into 1. So that is greater than, this value is marginally close to 1 or marginally greater than 1. Okay, or you can say that is marginally greater than 1 also. So you can see it is greater than 1. So as I said that I will consider it is safe if factor of safety is greater than 1. So that means it is marginally safe. So we can say, so marginally the liquefaction will not occur. Okay. So it is marginally safe. And as we are considering, if factor of safety is greater than 1, the liquefaction will not occur. So marginally safe. So I can say the liquefaction but remember that here we are not providing any factor of safety. Here if it is greater than 1 means safe. But if you provide a factor of safety say 1.25 or 1.5, then you have to check if, and you have to say if the factor of safety is greater than that value that you have chosen, then it is safe. Otherwise not. But here I have chosen only the 1 is my threshold value. That's why I am saying it is safe. But if you consider the 1.5 say, or 1.25 is your factor of safety or threshold value or factor of safety, then has to be greater than 1.25, then it is safe. Okay, so now I will use the next technique, that is the use of CPT data. Okay, so next problem is CPT, cone penetration test. So here the similar water table condition we will consider, similar unit weight of soil we will consider, but it does not mean that they are the same soil. These data are taken for different soil, but water table condition and unit weight are taken same for all the examples. Okay, so that means here we can see that if I take the CPT data and then we consider the same value, that means we are taking that my cone resistance, okay, that is 8300 kilonewton per meter square. Okay, then my sleeve friction, F, which is 76 kilonewton per meter square. Okay, and Max by G I have considered 0.25 and magnitude MW is taken 8. The depth at which I will check it is equal to 15 meter below ground level. Okay, and again the water table is 2 meter below the ground level, then gamma bulk is equal to 18 kilonewton per meter cube, gamma sat is equal to 20 kilonewton per meter cube, and gamma W equal to 10 kilonewton per meter cube. So now we have to check whether at 15 meter depth the liquefaction will occur or not. And as I mentioned, it is we have to give the CPT will give you the continuous data. Okay, so if you look at that CPT data I have given in my CPT lecture, you will get it's the continuous data. So that means for every depth or certain depth, so some certain interval, we have to check along the depth whether the liquefaction will occur or not, and then you will get the profile, like factor of safety profile along the depth. Then we can identify the zone of liquefaction. So here I will show you for a particular depth. The similar way you have to check it for other depths along the other points along the depth. Clear? So in the next class I will solve this problem. Okay, and then I will show you by using this data how I will get the CRR value, and from there how I will check whether liquefaction will occur or not by using CPT test or CPT data. Thank you.